Okay, so like I said in the last video, limits at infinity are horizontal asymptotes. Limit of f of x as x approaches infinity is L. In this case, the line L has to be horizontal asymptotes. Okay? And then you go in the other way, they could be the same or they could not be the same. Right? In this case, let me show you another example. We did this one analytically before, but if you look at it graphically, you can connect the horizontal asymptote here, and they were the same. Right? As x goes to infinity, we discovered it was 2. That goes to 0. And as you go the other way, as x goes to negative infinity, you still have positive 2, and that would be the horizontal asymptote for that function. They'd be the same in both cases, where in this example, they're different. Here's an interesting function. How would we do this analytically? What if I said do this without the graph? On your test, I won't let you use a graphing calculator, so I will say, because the graphing calculator makes it a lot easier, I would say find the limit of this function as x goes to infinity. Can you figure that out? It's kind of like there's not a whole lot of work to do here. Of course, I make you show all your work, and we'll have plenty of problems in this class where you have to do a lot of work to support your answer. In this one, if you're not graphing it, well, what work would I do? I'd probably break it up and look at two individual limits. And of course, this one's easy. The limit as x goes to infinity of something that's not changing is unchanged. And then I have to think about this one. This one's weird. Say, okay, sine x over root x. Well, sine x, and again, this is just from knowing what you know about trig and algebra. Your sine curve just goes up and down forever. It oscillates between 1 and negative 1. So what happens if you divide that by an ever-increasing value? It's going to go to 0. Right? This just goes between negative 1 and 1, up and down, up and down. But as you go, as x gets larger and larger and larger, you're dividing something going from 1 to negative 1 by an ever-increasing number. So the highest it could be would be like 1 divided by 1,000,000, 2,000,000, 1,000,000,000. Right? Even though you're square rooting x, it's still unbounded. As x goes to infinity, so does root x, just a little slower. And that's what this behavior is. It still oscillates, but it just gets smaller and smaller and smaller, and it's going to 0. So your limit there would be 5. Here's your, we looked at this one before, x cubed. So again, you could have horizontal asymptotes. You could have limits at infinity that exist, or you could have limits at infinity that don't exist, like in this example. And this is just the mathematical definition of an unbounded limit as x goes to infinity. And you got a bunch of those. Like I don't focus too much. You'll notice as like trying to remember all these definitions because it's not necessary, right? I mean, there's so many rules in algebra and calculus that if we don't really need it to apply to our problem, then we don't need it, right? If I say find the limit as x to the 5th, as x goes to infinity, I don't need you to go and say, oh, well, there is a property for power functions where if n is positive and odd, then I know that as x goes to infinity, so does y. But as x goes to negative infinity, so does y. Where if it's an even function, then they're both infinity or negative infinity if it's a negative x to the n. Right, then it's going to be upside down. That's just knowing that would be negative infinity, right? That's just knowing your functions and what they do. These are basic functions, basic polynomial functions. So I don't need you to memorize these. I don't want you to memorize these. I want you to say, well, oh, x to the 5th, that acts like x to the 3rd. It's an odd polynomial. So as x goes to infinity, so does y. And then as x goes to negative infinity, so does y. Okay, and here's rules again, like we don't need these. I don't think we need these rules. I think based on our knowledge of that function, we can find the limit. That function, if n's even or odd, we can find the limit. Rational function, that's easy, that's going to 0. What about this one? The limit of p of x. Oh, if there's some kind of constant, then we know it's going to depend on the degree of the polynomial. We'll come back to this one. Okay. Easy, right? Doesn't at infinity, doesn't matter, doesn't matter, doesn't matter. That matters. Even degree polynomial, up and up. Same thing here as we go to infinity, doesn't matter, doesn't matter. Focus on that. That's an odd polynomial that's negative. So we remember what happens. And if you don't remember what this function does at negative infinity, infinity, you can just plug a number in, right? If you plug in negative 10, then negative 10 cubed is negative. Negative times a negative is positive, right? And same thing over here. You can do some quick analysis by just plugging numbers in with your calculator, like a scientific calculator. So don't lean on your graphing calculator too much for these, because I want you to analyze these functions without looking at the graph. The graph is a good support, something to help us understand why that is. Like this one, for example. So if the graph wasn't here, how would you approach it? Say, find the limit as x goes to infinity of this function. Without the graph, you say, doesn't matter, doesn't matter. This is blowing up. Or if you want, you could simplify it, if it helps. It'd be 3 over x. Be equivalent to 3 over x, which is 0, right? This is blowing up and this is not. And that's where you get your horizontal asymptote, and that works from the other direction as well. Okay, this is the one we started with. You can see that limit, we took the limit and got 4, but it's also horizontal asymptote. All right, and you might remember these properties from algebra class. I always teach these in my college algebra class when we're studying rational functions. There's like, you can memorize the degree, right? The degree of the numerator is less, so that if this is a bigger polynomial than this one, then you have a horizontal asymptote at 0. That's algebra. But now calculus, you have the limit as x goes to plus or minus infinity to 0. It's the same thing. Okay, what if they're equivalent? That was like this guy. If they're equivalent, if the degree here doesn't matter, doesn't matter. If they're equal, you end up with a ratio of those guys. That's your horizontal asymptote. Learned from algebra class, but now it's also our limit as x goes to plus or minus infinity. And then what's the other case? The other case is if you have the degree of the numerator greater than the degree of the denominator, then it's going to be unbounded. Like, let's see, this one. Right here, the degree doesn't matter, doesn't matter, doesn't matter. Degree is higher in the numerator. So it's going to be unbounded, right? The denominator is growing a lot slower. The numerator is going faster. So as x goes to infinity, this one will go up. And it turns out in this case, you do have to think about it negative infinity, but it will also go up to infinity. Okay, so that's your connection there between algebra, rules for asymptotes, no horizontal asymptote, and now the calculus. Limit 0, just like the horizontal asymptote, limits the ratio of your leading coefficient, just like horizontal asymptote. There is no horizontal asymptote if the degree in the numerator is bigger, limits unbounded. And then we can talk about a slant asymptote as well. For example, if it's just 1 degree higher that is in the numerator, then you would say, oh, it's unbounded. Okay, so that's really, here's an example of that. If we didn't have the 1 degree higher, we would just say the limit at infinity of this function, the limit as x goes to infinity of this function. I would say, well, wait a minute. If those don't matter, this thing's really blowing up at infinity. So that means the limit's unbounded. Okay, I'm not going to ask you for the horizontal asymptote. We could dive into that, but I just want the limit. Okay, so that one really just kind of follows this rule. Degree of numerator is greater. And then, of course, we have vertical asymptotes. But that's just a kind of a separate concept. We already know how to find those, right? If I give you a function, let's see, the vertical asymptote here would be, it's a different topic, right? This is the limit, as x goes to infinity, I got limits. That's what we're really talking about now. But we can say, well, wait a minute, since we're dealing with rational functions, there may be a vertical asymptote, right? And that's you get those from just figuring out what the zeros in the denominator are, right? So in this case, this function is undefined where? You remember this from algebra class 2, x plus 2. The domain is x cannot be negative 2. That's a vertical asymptote as long as there's not a factor of x plus 2 in your numerator, which there's not in this case. So I know that without calculus. Vertical asymptote at x equals negative 2. Assuming f is reduced form. See, this isn't a calculus definition that your textbook's giving you. Vertical asymptotes occur at zeros of your denominator.